Continuing on with class 11, here is sample problem 4.4. I'm going to do this in class as sort of like an in-class assignment type of quizzy dealy, but let's do it here and as a video. Oh, excuse me. All right. This is a frame of some point, and I think it looks like it's holding up a roof. Okay, of a small building. Knowing that the tension in the cable is 150 kilonewtons, determine the reaction at the fixed end E, right? So you might not be able to tell, but this is a cantilevered joint right here, so it has to sustain a moment. I think a lot of times this would be a pinch joint, but there is a moment by the way that this thing is fixed. One thing that I might want to do to start with is get some geometry out of the way. I'm going to figure out what that angle is, and what I find is, well, I add these two together, by the way, that this is going to be 6 meters, 2.25 and 3.75. And if I take the inverse tangent of that 4.5 divided by 6, I get a 36.87 degrees, which also tells me, I recognize that must be a 3-4-5 triangle, by the way. And then I'd like to break the force into components. It's just a nice thing to do. So we have this force that's on there. I'd often call that Ft, but I could say that Ft in the x direction is going to be that 150 kilonewtons times the sine, in this case, of 36.87, which ends up being an even number because I think that's going to be the 3/5 of the thing. And then similarly, that Fty is going to be our 150 times the cosine 36.87 degrees, and so we end up with 120 kilonewtons. Now, I put together my FBD, draw a nice sketch of this thing. And I might include that cable. All right, that's internal right there. That cable doesn't do anything, just to be clear. And it's kind of obnoxious that they put these four forces there and there. We also have a force coming this way and a force coming this way down here. So this is the 20 kilonewtons and 20 kilonewtons and 20 kilonewtons and 20 kilonewtons. And this force is the 90 kilonewtons, and I'll put this one over here is the 120 kilonewtons, and I have all the loads applied. Now I put the reactions. We're going to have, they said that this was E, so I call this REY, and I'll choose this one as the REX, and I just assumed positive right here. Same thing for here. I don't know which direction this moment is going to go, so I'm going to call this ME and stick it right there, and hopefully we'll be able to figure out, we select as a default as positive. And I'll put in some the 1.8 meters in here in between each, just to help me remember. And then this is not good dimensioning, but I'll shove him in there. There's the 6 meters that we care about. And I think I have everything, except that I didn't do my declaration of FBD and declaration of directions. Now I have a fully labeled FBD. So I'll take my sum of the moments about E. I could do some of the, I could do some of the forces also. I don't rely on the sum of the moments. A lot of times I'll need the sum of the moments in order to do the sum of the forces. In this case, it doesn't, because we're just looking for a reaction moment as part of this. So as we march through the thing, It's just noting that 1.8 times 4 is 7.2, 1.8 times 3 is 5.4, 1.8 times 2 is 3.6, right? So we can just quickly go through. These are all counterclockwise about E. So that's 7.2, 20 times 5.4 plus 20 times 3.6 plus 20 times 1.8. Then we look up at that the forces of the cable. That 120 passes right through E, so we can ignore him. And that 90 kilonewtons is perpendicular there to the 6 meters, and it's going to be clockwise. So that's 90 kilonewtons times 6. And then we also have the reaction, which we've drawn as positive, and it all equals to 0. And by the way, don't get confused. Maybe I should, I haven't done this before, but maybe I should stick an R in there or something right there. That's the reaction moment, right, that we're actually calculating. So that you don't get it confused where I do the sum of the moments about E up here, right? That's an ME, and then I put this ME in here, and you get confused that I'm just solving for ME. But no, we want to make sure that we put ME as an actual thing inside an equation that's described by this. So we say we do all this, and we solve, and we get a positive 180. And these are kilonewton meters. Careful with the units. But they're positive. Therefore, that positive guess was correct. Right, and so that's counterclockwise was what we guessed. So that's part of the reaction, right? So that's the total reaction. We also want to do the sum of the forces in the x direction equals 0. And then so we say that it was going to be REX right there, right? And it's drawn as positive. And then the only other horizontal is that 90, and that's positive. So we can see where this is going. And it's supposed to be 90, not 96. It looks like a 96. We can see that REX is equal to negative 90 kilonewtons, which we know is therefore the other direction. So Rex is going to be 90 kilonewtons, and pointed that way is our actual answer because I want it with an arrow. And then the sum of the forces in the y direction. A little bit more things. Upwards is positive. So we go. We see there's 4 of them, so I'm just going to have 4 of them times, and they're negative. Negative here. And then we're also going to have a negative 120. And then the reaction. It's the only other vertical one that's going to be drawn as positive, so we keep it as positive. So REY is, we add all those things up and we get 200 kilonewtons, and it's positive. So there you go. We got the reactions. Make sure we're taking a look at what the book has and their solution method to it. But that's another one bites the dust right there. Another solution to a free body diagram to get reactions at a point, and then this is a fixed point kind of thing. So let's see. 8-minute video.